Okay, let's finish up this lengthy section 3.1. And the big result and lengthy proof involves showing that the definition we have for determinants of a square matrix is the same as a definition you had in sophomore linear algebra, which was probably something in terms of expansions by cofactors. You got used to an iterative computational process. You saw that you could expand along any row or column, so you took advantage of that by looking for zeros. Here, we've done this stuff with these permutations. So the plan is to take what we've done and show it's equivalent to probably the recursive definition that you had in linear algebra. So determinants were defined recursively in terms of cofactors. We'll define cofactors here shortly. We look at minor matrices and determinants of those minor matrices, and that's what leads us to cofactors. Meaning, if you want to take the determinant of a 5 by 5 matrix, you're going to have to take 5 determinants of 4 by 4 matrices, each of which involves 4 determinants of 3 by 3 matrices, each of those of which involve 3 determinants of 2 by 2 matrices. So that recursive nature of the definition of determinant from linear algebra was why it was so computationally complicated to actually calculate derivatives by hands. And that's why you like having shortcuts, like using some row reduction stuff. Okay, so to link together what we're doing and what you did back then, take A to be a square matrix with entries lowercase a sub ij. We're defining a new matrix, capital A sub ij, matrix A sub ij. This represents the n-1 by n-1 submatrix of A attained by eliminating the ith row of A and the jth column of A. So the subscripts in the capital A in this matrix represent the row and column, respectively, of the original matrix, n by n matrix A, that have been eliminated to produce this matrix. I'm used to calling this matrix itself a minor matrix. I don't think I quite found that terminology in Gentle's book. He does refer to a minor element. But this is commonly called a minor matrix of matrix A, one obtained by eliminating one row and one column. The determinant of that capital A sub ij is called the minor of element A sub ij. And when you put a sign on it, the sign being -1 to the I plus j, so it's dependent on even and oddness of these indices, then this number is called a cofactor of A sub ij and denoted as alpha sub ij. Okay, so minor matrices are probably familiar to you. Minor element, I don't know so much about that, but certainly cofactors. Minor matrices and cofactors is probably how you dealt with determinants in linear algebra. And what you saw in sophomore linear algebra is the following. We can calculate the determinant of a matrix A, usual notation. It's a new thing is these cofactors, the alpha sub ij's. We can calculate the determinant of a matrix A by summing j equals 1 to n, A sub ij, alpha sub ij. And this is valid for any I between 1 and n. Okay, so in this summation, the i's don't change. The i's represent, let's get that formula a little bit bigger. The i's represent rows. So what we're doing is summing along the ith rows, or taking a summation involving the ith row of matrix A and the associated ith row cofactors. Oh, we could sum along the jth column as well. So this is the same thing you see in sophomore linear algebra, probably is a theorem there as well. The book I like to use for sophomore linear algebra defines determinants by expanding along the first row. I think that's a common approach. And we're going to kind of mimic that approach in the proof of this theorem. But then you learn that you can, in fact, take cofactor expansions along any row. That's what this formula is about, or any column. That's what this formula is about. Here the i's change, here's the j's change. So you can calculate determinants along any row or any column. How convenient if we've got a row with a bunch of zeros in it, or a column with a bunch of zeros in it. Or if we could introduce a bunch of zeros using row operations and apply some of the stuff we've seen earlier. Okay, let's go through, sit tight, a proof of theorem 3.1.f. And what we must show for our proof of this is, hey, we're computing determinants in terms of those symmetry groups and all those permutations. So we had to show that that gives the same thing as this formula here. This, actually, when I equals 1, this is probably your definition of determinant from linear algebra. We're going to go through and show our definition of determinant with all those symmetry groups and permutations is the same thing you get when I equals 1 here. And then we'll prove the more general result, that it in fact holds for all I, this equation 5.1, and equation 5.2 holds for all j. This is going to take a while. Okay, so plan is to show first this result for I equals 1. So we're going to establish equation 5.1 fixing I as 1. And then we'll take care of the rest of the values of I after that. But that's probably about 2/3 of the theorem is establishing that. Okay, let A sub ij be that n minus 1 by n minus 1 matrix formed from matrix A by eliminating the ith row in the jth column of matrix A. All right, consider equation 5.1 when I equals 1. Okay, denote by lowercase a sub ts superscript parentheses j. Probably I made that notation up because it's so clunky. Denote the tth element of matrix A sub 1j with these symbols here. It's going to be a little while before we make too much use of this, but what I'm doing is labeling the entries in this matrix. I would call it a minor matrix, A sub 1j, the entries as lowercase a sub ts. Putting a superscript j on there because this matrix, capital A sub 1j, is, in a sense, this is a function of parameter j. So I want that parameter to appear in the symbol that represents the elements of that matrix. All right, so then what we have is the t and s's ranging from 1 to n minus 1. Here's the big problem. The only difference in this matrix, A sub 1j, and matrix A is that we've eliminated the first row of A and the jth column of A to produce this matrix, right? We took I equal to 1, right? So we've got capital A sub 1j, I equals 1, it's the first row, the 1th row that's been eliminated, and the jth column. But there ain't a whole lot of difference between matrix A and this minor matrix. It's gonna be very, very tedious for us to go through and look at the determinant of A as it relates to the determinant of this minor matrix. We're going to have to go through and take our definition and relate it to a determinant of a minor matrix, and that's what these cofactors are. And in so doing, we're going to have a bit of a mess, really, with the indices. Now, if I step back and look at it, the big picture isn't so bad. It's the tedious details, as often happens in matrix theory, that's going to make this thing take us probably 20 or 30 minutes to get through. Okay, so just notation, A sub ts super j, well, those are the elements of the matrix capital A sub 1j. Okay, the determinant of matrix A, new problem, that's our definition. you sum over all permutations, excuse me, in the symmetry group S sub n. You take the sign of those, the sigma of those permutations, and then you take the product. Remember, a sub 1 something, a sub 2 something, a sub 3 something, up to a sub n something. Something's being determined by the permutation. Okay. When I equals 1 and we let pi range over S sub n, these pi sub i's are going to range over the set 1 through n. So we'll get all of those values out multiple times. There's a bunch of these permutations. There's n factorial of them. Oops. Sorry, I'm at the wrong spot, wrong button. There we go. So what we're going to do is define an S sub n super J. It's a subset of S sub n. I'm not saying it's a subgroup of S sub n. It's a subset of S sub n. I suspect was it ever a subgroup? Possibly for one of the J values, it's a subgroup. Not our problem. I'm just partitioning up this set of permutations. So we're defining S sub n super J as all permutations in S sub n that map 1 to J. So that's what the superscript indicates. The permutations in S sub 1 super J all map 1 to J, and they map the remaining values 2 through n to the values 1 through n, except for J, because 1 is mapped to J. So we've lost 1 as an input value, and we've lost J as an output value in one of these permutations. All right. So what we're trying to do is shift the conversation from the determinant of an n by n matrix in just a little bit to a conversation about an n minus 1 by n minus 1 matrix. All right. So that's why we see we've lost one thing here and we've lost one thing there. We've lost 1 from the inputs and J from the outputs. Okay. So when we look at such a permutation in this S sub n super J, we're effectively looking at permutations on a set of size n minus 1. It's not exactly a permutation because we put in any of these n minus 1 things and we get out any of these n minus 1 slightly different things. When there's a 1 in the second set, not in the first. There's a J in the first set, not in the second. So it's not legitimately a permutation, but I can count permutations, and there's going to be n minus 1 factorial of them. So the cardinality of S sub n super J is n minus 1 factorial. How many of these S sub n super J's are there? Well, there's 1 for every J between 1 and n, so there's n of them. So if I were to count how many elements we get as J varies from 1 to n, we get n minus 1 factorial n times. We get n times n minus 1 factorial, that's n factorial. Yeah, and that's the order of the symmetry group S sub n. So the numbers seem to balance appropriately. Okay. In fact, what we're doing is taking S sub n and partitioning it into these S sub n super J's. All right. And that counting argument has suggested that this is correct. So let's take the determinant of matrix A. We're used to seeing that as a single sum over all pi in S sub n, sigma of pi, product from I equals 1 to n, a sub I, pi of I, a sub I, pi of I. Well, we've written it as a double sum because we've taken that S sub n and partitioned it into these S sub n super J's. So instead of having a single sum over all of S sub n, we could take a sum over one of these S sub n super J's and then let the J range over its values of 1 to n. So instead of having a single sum of n factorial things over the group S sub n, we've got n sums over, how many of these are there? N minus 1 factorial. So we've got n sums of n minus 1 factorial, which altogether produces an n factorial sum. So it's the same summation. We've just shifted from S sub n to these things here. I really want to shift from S sub n to basically to S sub n minus 1, because we want to talk about some determinants of minor matrices, n minus 1 by n minus 1 matrices. But all we've done here is notationally shift from elements of S sub n to elements of these S sub n super J's. Okay, so that gives us something of this sort, double summations there. Hey, if pi is in S sub n super J, then pi of I, well, pi of 1 I know, pi of 1 is J, because that's what S sub n super J is, permutations that map 1 to J. So when we plug in I equals 1, we're going to get out J. So A sub 1J is what we get out when this permutation pi comes from S sub n super J. So let's take that A sub 1J and bring it out. Factor it out front, and then multiply the remaining I equals 2 through I equals n terms together, because pi of 1 equals J. All right, that's a step forward. This is a product of n minus 1 things. And I want to get to a product of n minus 1 things. It's got a sigma out front. It's got something else out front as well. And I like the A sub I stuff. And I kind of like the pi of I stuff, but we got to get out of this S sub n. We got to get to something involving a symmetry group on n minus 1 letters to recognize determinants. So we've modified things a little bit. Still is not quite the right setting to talk about determinants of minor matrices, and it's going to be a couple of slides, maybe 3 slides before we get there, to talk about minor matrices. But we're in a neighborhood. Means I got a permutation, and this permutation, you know, it kind of effectively moves n minus 1 things around. It moves these n minus 1 things around. I know what it does to 1. I mean, that's where it came from. And we've got a product here involving here n minus 1 things. So yeah, we're in the neighborhood of seeing determinants of an n minus 1 by n minus 1 matrix. Okay, hey, this A sub 1J, we can bring that out front of this summation. It's dependent on J, and J varies out here in the outermost summation. So we can bring that outside of this innermost summation, put that constant here. And this looks even a little bit more like a determinant. It's not, because I want to see a product from 1 to n minus 1. And I want to see these permutations come from a symmetry group on n minus 1 things. Indices are wrong, off, we'll adjust them. I just need to shift them back by 1 each. You'll see us do that. And these permutations are kind of not from the right symmetry group. So that, but other than that, this looks a little bit, actually a fair bit, like a determinant of an n minus 1 by n minus 1 matrix. Indices are off and something funky with the permutations. In the next few pages, we're going to deal with that in vulgar detail. And when we get done, we ought to see a sum of permutations in a symmetry group on n minus 1 things, sigma of those permutations, and then a product from 1 to n minus 1. So that's the goal in what follows. Okay, we'll hark back to this equation here in a little while. As I said, permutation pi ranges over the S sub n super J's. And the elements, A sub I, pi of I, range over all the entries in A sub 1J. So we do get all of the A sub TS super J's. Just coming by for a brief visit. We won't see this guy again for a couple of slides. But we've denoted those entries of A sub 1J as A sub TS super J. So as I ranges from 2 to n, then we get these elements to range over all of these elements. Remember, T and S range from 1 to n minus 1. It mentions it for T right here. T ranges from 1 to n minus 1. Only problem we've got is I ranges from 2 to n, and we want T to range from 1 to n minus 1. Okay, T is missing this last N value, and I is missing the first value of 1. But other than that, it's the same number of numbers. Okay. So what we're going to do is reindex the product and that inner summation. That was the one over the S sub n super J set. And we'll reindex from 2 to n for pi in S sub n super J to a new permutation, gamma, and T between 1 and n minus 1. So we're trying to get, like I told you, trying to get the indices to run from not 2 to n, but 1 to n minus 1, and trying to get the permutation to come not from S sub n, but from S sub n minus 1. All right, so we're going to do a bunch of introducing of permutations and computations of those permutations to get this done. This will be tedious. The big picture, though, is, dude, I'm just reindexing and trying to make it look like a determinant in the appropriate setting for an n minus 1 by n minus 1 matrix. Okay. So we'll just take T and define it to be I minus 1. Yeah, just reduce these by 1, and that changes the I values into the T values. And we're defining gamma in S sub n minus 1 as follows. The gamma of T equals pi of T plus 1, that actually be pi of I, as we'll see shortly, if pi of T plus 1 is less than J. Define gamma of T to be pi of T plus 1 minus 1 if pi of T plus 1 is greater than J. All right. What's coming out of these pi functions, remember, is, see, we were getting out, well, out of the pi function, we're getting out 1 through n. We want to skip J. We're working on skipping J in this gamma of T thing. Remember the indices we had, let's look at the previous page. Previous page. Here we go. We were taking 2 through n, and we want to map them from 1 through n except for J. So that's the motivation in the definition of T and the definition of gamma. So, hey, 1 through J minus 1, when we're getting output that's less than J, I'm happy with that. When we're getting output bigger than J, I'll shift that back by 1. Because I want to get out with this gamma function, I want to get out 1 through J minus 1, J plus 1, up through n minus 1. So we're really just shifting this last bunch of outputs back by 1, so that the total output of that gamma function will run from 1 through n minus 1. We subtracted 1 from each of these. The input will range from 1 to n minus 1, and the output will range from 1 to n minus 1. That's why we're defining gamma in this piecewise way. That means gamma maps 1 through n minus 1 to 1 through n minus 1, as I just observed. Oh, that means gamma is an S sub n minus 1. So it's a legitimate permutation in a symmetry group of the right size to use it in talking about the determinant of an n minus 1 by n minus 1 matrix. Additional little observations, we'll use this on down the road. We got I equals T plus 1. I solve for I in this little equation. So this is really gamma of T in terms of pi of I. So we've got gamma of T equals pi of I precisely under these conditions when pi of I is less than J. And we've got gamma of T equals pi of I minus 1 for the minus 1 stuff there when gamma of I is greater than J. Yeah, these gammas and pi's agree when the numbers aren't too big. But when they get bigger than J, we won't pull them back by 1. And that's what's being accomplished exactly here. Okay, so we're trying to go from pi's in S sub n to gammas in S sub n minus 1. All right. To bridge the gap, we're going to define a new permutation, gamma prime, that lies in S sub n. And what we're going to do is just let it be the same thing as gamma, but I need now to define the gamma prime for n. Remember, gamma is only defined on 1 through n. So to define gamma prime in S sub n, we'll let it on 1 through, let's say it correctly, gamma is defined on 1 through n minus 1. Okay, so we'll let gamma prime do the same thing that gamma does on 1 through n minus 1. And we'll define gamma prime of n. Now we've got something that's defined on 1 through n. Gamma prime has to be defined on 1 through n. And we'll define it to be output n. Remember, gamma itself has input 1 through n minus 1 and output 1 through n minus 1. So we're missing n both from an input and an output in a sense. So when we define gamma prime, take the input of n and give it n as an output. And that'll allow you to extend gamma to a permutation on 1 through n, not just 1 through n minus 1. The important thing here is, hey, we just threw in a fixed point. The sigma values for gamma prime and gamma are the same. If I write gamma as a product of transpositions, treating it as an element of S sub n minus 1, that same product of transpositions will produce gamma prime. So their sigma values are the same. Their even and oddness is the same. The only difference is, hey, for gamma prime, I've got this additional fixed point that gamma doesn't even address, but fixed points don't introduce transpositions. Or if you like, I could introduce it as a product of 2 transpositions. But think of fixed points as no transpositions. And we get the parity is the same. All right. We want to relate the gamma primes and the pi's. The way we've done this, remember we had gamma defined in terms of pi's. We get gamma prime of 1 as pi of 2. Gamma prime of 2 is pi of 3. Gamma prime of n minus 1 is pi of n. And gamma prime of n is pi of 1. We knew pi of 1 was j. All right. So the gamma primes and the pi's are related, if you like, through this mapping. Now, we've eliminated the jth column of matrix A when we created the minor matrix, capital A sub 1j. And that's what we want to kind of kick over to the side. We want to, at some point, we'll need to move a jth term to the right-hand end. And what we'll do is keep the first j minus 1 entries in the same place, more of this in a second, and we'll click j plus 1 back to j, j plus 2 back to j plus 1, n minus 1 back to n minus 2, n back to n minus 1, but we skipped over j and we didn't get to n. So we'll map j to n. So you're effectively, the way we'll use this, is moving a jth term to the end. We're going to move it to the end and then we're going to cut it off, is informally what's going on with these permutations. Because we're trying to get rid of that jth column and get to a setting where I can talk about permutations on the symbols 1 through n minus 1. All right. So here's what we're going to do. First, we'll increase the indices by 1, mod n. So we'll map 1 to 2, 2 to 3, n minus 1 to n, and n back around to 1. That can be accomplished with, it's actually a cycle. Cycle can be written as a product of these permutations. We're going to need to know how many permutations there are here because we're going to need to know sigma of this permutation. I've called pi prime here in a little while. Let's see, there's 1, 2, this would be what? The n minus 2 permutation. First one, got a 2 there. Second one, got a 3 there. So which one is this? It'd be a 1 less than this, be a n minus 2. Here's the n minus 2 transposition, and here's another one. So there's a total of n minus 1 transpositions here. So when we go calculate the sigma value, sigma of pi prime, it'll be -1 to the n minus 1 power. Even or odd determines positive or negative. All right, so first we'll do that. Second, we'll apply permutation pi. And third, we'll perform this mapping here where we move a jth term over to the end. So by doing those three things, applying pi prime, applying pi, and applying pi double prime, will produce the gamma prime mapping. All right, the pi double prime was this mapping where we took j to n. I'm going to need to know the sign of it as well. Pi, I don't know. I don't know sigma of pi. I'm going to need to know sigma of gamma prime, and that's going to be related to sigma of pi. That's where we're going on this. All right, this permutation, how about you trust me, can be written as this product of transpositions. I need to count them. Let's see. And we go, here's a n minus 2, n minus 3, n minus 4, down to j. So how many you got here? They range from j up to n minus 2. So I want to count the number of transpositions. Forget this last one for a second. That'd be the big number minus the little number. This would be n minus 2 minus j. Oh, well, plus 1, because that's how you count stuff. So if I've got these consecutive numbers, which we do, how many numbers are there? Big one minus little one plus 1. So we'll have n minus 2 minus j plus 1. That'd be n minus 1 minus j. And then we've got this extra one giving us a total of, where were we? I think it's probably n minus j transpositions there. There are. There's n minus j transpositions here. So if we want to go and find the sigma values of these relevant permutations. Sigma of pi prime, okay, last slide we counted those. There were n minus 1 transpositions, so sigma of pi prime is -1 to the n minus 1. Tried to talk you into the fact that here there's n minus j transpositions, so sigma of pi prime, this is pi prime, is -1 to the n minus j. So if we want to find sigma of gamma or sigma of gamma prime, a couple slides ago we said these two quantities were equal. They only differed by the fact that this has an extra fixed point that gamma doesn't have. So in terms of transpositions, their sigma values are the same. Sigma of gamma prime would be sigma of pi double prime, pi prime, because we built those pi prime and pi double prime so that this equality would hold. We're just counting up numbers of transpositions. So all we've got to do for a sigma of a product of permutations is the product of the sigma values. It's plus or minus 1. I'm just trying to see if there's an even or an odd number. The sigma of gamma double prime, okay, we had that one here, n minus j. Sigma of gamma prime, we had that one here, -1 to the n minus 1. So I'll multiply these two together, giving us -1 to the 2n minus j minus 1. Yeah, -1 to the 2n minus j minus 1. I don't really know anything about pi, so I still got the sigma of pi as an unknown. We can drop that 2n, and that we're taking powers of -1. So we get -1 to the negative j minus 1. That's the same as -1 to the positive j plus 1. If negative j minus 1 is even or odd, then so is j plus 1. It's negative. The negative of a number has the same even and oddness. So let's write it as j plus 1, just because it's cleaner. You like negative j minus 1, go right ahead. But I'm going to want to see it written like this down the road when we're trying to match up some parameters. All right, so the punchline here is sigma of gamma, or gamma prime, is the same as -1 to the j plus 1 sigma of pi. Okay, so yeah, there's the punchline. So that equation star we had upstairs, for the record, here it is again. We had the determinant of A written in terms of this, where we had introduced the S sub n super j's. We're really trying to get rid of those guys. I want these indices to run from 1 to n minus 1, not like the I values do, but the T values will. And I don't want to see A sub ij's. You know what I want to see? I want to see A sub st super j's. I want to see entries of the minor matrix capital A sub 1n. That's what we're going for. So I want to see S's and T's here. And I want to see, you know what? I don't want to see pi's. I want to see gammas. I want gammas down here because those gammas, they live, this is on the previous slide, they live in S sub n minus 1. So if we can get permutations down here in S sub n minus 1, and we can adjust this so that this runs from 1 to n minus 1, we got ourselves a determinant of an n minus 1 by n minus 1 matrix. So that's the big picture. All right. So how we doing? Sigma of pi. Okay. I know what sigma of pi is in terms of the gammas, so we can substitute that in there. Next slide. Okay, so we've done exactly that. In addition, I want to take those pi's and replace them with the gammas. So we've gone from pi in S sub n super j. We've set things up where gamma prime is related to pi by this relationship. The gamma primes are from S sub n, but all we've got to do, back to the next page, is restrict gamma prime to 1 through n minus 1, and then that gives us an element of S sub n minus 1. Hey, we had n mapped to n under gamma prime, so we set it up. I needed to transition from S sub n to S sub n minus 1, and this is where we're doing it. So we take the pi's, replace them with these gammas. We saw computationally where this came from. We had, what was it, t equals I minus 1. Make that substitution. That'll allow you to translate the indices from t equals 1 to n minus 1. I'll look at the entries of matrix A. We had gamma of t corresponding to pi of I, wasn't it? So we can convert that previous stuff. Let me go back to the previous slide one more time. We had the a sub I, pi of I stuff. We get that translated into a sub t, gamma of t, super j. Sorry for all the superscripts. But this looks almost exactly like a determinant, only a couple more lines. We've got gamma in S sub n minus 1, sigma of gamma. We've got this product stuff. There's the t gamma t thing. It reads a sub 1 something, a sub 2 something, up through a sub n minus 1 something. Something is determined by the gammas. It's of the right format. We got this thing in the way, but we'll shift it out next. Okay, so next, bring the -1 to the j plus 1 stuff out front. All right, and now you're left with, finally, a sum over gamma and S sub n minus 1, sigma of gamma, product from 1 to n minus 1, a sub whatever, gamma of the whatever. These were entries of, what was matrix A sub 1j. That's why I introduced these symbols. So this is exactly the determinant of matrix A sub 1j. We had to go through all this stuff. Remember, all these extra permutations just to get that pi from S sub n translated into a corresponding gamma in S sub n minus 1. That being done and some other indices shifted around, this looks exactly like a definition of a determinant. So there you go. What have we got here? Oh, hey, look at this. We got -1 to the j plus 1. Told you I wanted to write it as j plus 1. That's times the determinant of a sub 1j. Hey, if we took -1 to the power, this index plus that index, which we have here, determinant of an a sub ij, that would be a cofactor. It'd be the cofactor alpha sub 1j. So what we have here is a sum from 1 to n, a sub 1j times alpha sub 1j. That's what we were looking for. This is a cofactor expansion along the first row of matrix A. And it equals, we got into this mess by starting with the determinant of A. So the determinant of A equals this thing here. That claim was equation 5.1. That equation holds when I equals 1. Okay, so that's the bulk of the work in this thing. Now we need to show, well, does it hold when I take sums along other rows other than the first row? Of course it does. Here's why. Okay, So take that equation 5.1 that gives you the determinant as a cofactor expansion along the ith row, and suppose I is greater than 1. Let matrix B be formed from matrix A. Right, so we're done with a permutation talk for the most part. We're going to use properties of determinants, about time. We've got several properties of determinants as they relate to elementary row operations, pretty much. So let matrix B be an n by n matrix formed from matrix A by interchanging in the following order. Interchange the I minus 1th and the ith rows. Interchange those two rows. You've backed the ith row back into the I minus 1 position. Then interchange the I minus 2th row and the I minus 1th row. Okay, now you've backed the ith row back into the I minus 1 position, then back into the I minus 2 position. What we're doing is swapping things and moving that ith row to the top, because we were just talking about using the first row to calculate determinants. And continue that process of swapping things two at a time and working that ith row up to the top of matrix B. The final swap will be swapping the first row and the second row. In so doing, the first row of matrix B will be the ith row of matrix A, and the second row through the ith row of matrix B will be the first row through the I minus 1th row of A, when you've effectively just shifted those down by 1. So, how many row interchanges did we have? I minus 1, I minus 2 down to 1. I count those up. It ranges from 1 to I minus 1. We had a total of I minus 1 row interchanges. Okay, well, you know, Theorem 3.1.c, how row interchanges affect determinants by factors of -1. So we get the determinant of A is -1 to the I minus 1, determinant of B. We're in the ballpark. If I is odd, then we've got an equality. All right, but we want to deal with this in terms of those formula. We got to work our way back to cofactors and formulas at some point. Let B sub 1j be the n minus 1 by n minus 1 matrix obtained by eliminating the first row and jth column of B. Let lowercase b sub 1j be the entries of that first row, the jth entry of the first row of B. All right. Claim is matrix B sub 1j equals matrix A sub ij. So let's see, how are we doing on columns? You ought to believe me on columns first. Matrix B, we've taken the rows of A and moved them around. So anyhow, when I eliminate the jth column of B, I'm eliminating the same entries, they may be in different places, but the same entries that are in the jth column of A. Now about the rows, in matrix B, we're eliminating the first row. In matrix A, we're eliminating the ith row. But the first row of B is the ith row of A. So by eliminating the first row of B, you're eliminating the entries that were in the ith row of J. That's how you made matrix B. So that's why we can claim B sub 1j equals A sub ij. They're both the same size, they're both square matrices, n minus 1 by n minus 1, and they get the same entry in the same relative locations. Okay, so if we take the determinant of A, we already observed that thing about the row interchanges. That's -1 to the I minus 1 times the determinant of B. Hey, the determinant of B, we can use what we already know about writing the determinant of B in terms of a cofactor expansion using the first row, the B sub 1, the first row of matrix B. That'll require this determinant of B sub 1j's. All right, that was part 1. If you like, I might call this maybe beta sub 1j. These would be the cofactors of matrix B. But we have that formula established when we use the first row. That's the one thing we've shown so far. So we're applying the previous result about determinants of matrices expanded along the first row. We're applying that to matrix B, not matrix A. Okay, so we get something like this. But wait a second. You know, B sub 1j is the same as A sub ij. Columns, same. You've moved the ith row of A to the first row of B. So I know B sub 1j, the entry in the jth column of the first row of B, is the same as the entry in the jth column and ith row of A. And that's how matrix A was related to matrix B. We still get these negative ones to the 1 plus j deals. You know B sub 1j and A sub ij are actually the same matrix. So the determinant of B sub 1j is the same as the determinant of A sub ij. And let's see what we got here. What's this? Never mind the negative 1 stuff. Looks like cofactor expansion. Not quite. Cofactor expansion would be sum from j equals 1 to n, so it'd be an expansion along the ith row of A. Remember, that's what we're working on. A sub ij, we should have negative 1 to the, the exponent here should be the sum of these two indices here. And the ij's here should be the same as the ij's there. So it's close, except the power of negative 1 isn't right. It should be negative 1 to the I plus j. Wait a second. If we take this and distribute it inside, there you go. Distribute that inside, since it happened a little fast. Add exponents, I minus 1, 1 plus j. The 1 and the negative 1 cancel. You're left with I plus j, negative 1 to the I plus j, negative 1 to the I plus j. Oh, that's it. Sum from j equals 1 to n, A sub ij. This is a cofactor. This is alpha. This is alpha sub ij. So the determinant of A can be computed in terms of cofactor expansions along the ith row as well as along the first row. So here's where we are in establishing this. We've established the first equation. You know what? Let me jump back to the notes real quick. Here's a statement of the theorem. We've shown this. Summing j equals 1 to n with I fixed. It could be anything. We first dealt with this formula when I equals 1, and we just now dealt with the case when I is greater than 1, between 2 and n. Now we need to go down here. This is where we're computing determinants by letting I range from 1 to n and keeping j fixed. So this is a cofactor expansion along the jth column of matrix A. We get that done, and then we're done with this. Okay, so consider that second equation. We're going to do some stuff with transposes because that interchanges rows and columns, and we'll just keep up with the indices as appropriate. And this part, thankfully, isn't quite as bad. All right. Notice that the matrix formed by eliminating the jth row and ith column of A transpose is A sub ij transpose. Eliminating jth row and ith column from A transpose is the same as eliminating the ith row and jth column of A itself and then transposing. So that should be at worst plausible. That's the relationship we get by this particular type of elimination. So I can relate these eliminated rows and columns in terms of transposes. We need that because we want to interchange the roles of rows and columns. All right. So the cofactor of the jth element of A transpose would be negative 1 to the sum of the indices times the determinant of the appropriate minor matrix, which we're claiming is A sub ij transpose. The transpose is in there. We've got equality of A sub ij transpose and what we would get by taking A transpose and then eliminating the jth row and the ith column. And that's what we need there to talk about cofactors. What you know about determinants of transposes, same as the determinants of the original matrices. First thing we showed with this determinant stuff in Theorem 3.1.a. So we can take the transpose matrix and replace it with the, as it were, original matrix itself. And now we've got negative 1 to the I plus j, determinant of A sub ij. That's exactly the cofactor alpha sub ij of matrix A. All right, so we're relating cofactors of A with cofactors of A transpose. The jth element of A transpose is the ijth element of A itself. So using equation 5.1, expansion for the determinant of A transpose along the ith row. So I'm doing it in general this time. Determinant of A transpose, of course that equals a determinant of A by that theorem. Determinant of A transpose would be a sum from j equals 1 to n, A sub ij prime, alpha sub ij prime. So we're expanding along the ith row. We know the row result. That was equation 5.1. We know the row result. We're applying that to A transpose. I'm using primes to give me the entries of the A transpose. Probably just me with that notation. So what we get then is the A sub ij prime is A sub ji. So remember, I'm looking at A transpose. So what we actually get for this first entry would be AJI. In terms of the alpha sub ij prime would be -1 to the I plus j determinant of A sub ij transpose, because we're looking at the transpose. This quantity sounds familiar. We were just talking about that up here. Different order on the powers, j plus I versus I plus j. Otherwise, everything's the same. That doesn't change anything. And it turns out that's alpha sub ij. So this quantity, in fact, equals alpha sub ij. We'll see that here in a sec, but let's see, want to take the i's and j's and invert them. It's buried down here in the fog, but we're going to change that. Let's change that to a sum from I equals 1 to n of A sub ji alpha sub ji with the primes. So we've interchanged the roles in I and j. They both range from 1 to n. They're dummy variables, so it doesn't matter. Interchange them. All right, I'm trying to relate this to the original matrix A. So we've changed it into a question about A transpose. Now we're trying to change it back into an answer about A itself. What's up with A sub ji prime? A sub ji prime would be the same as A sub ij. So we can get an A sub ij there. I interchange the i's and j's here. So we'll do that next. Interchanging the i's and j's. So I got the A sub A sub ij here. We've interchanged the i's and j's in this second part as well. That gives us a determinant of A sub ji transpose. Well, let's observe the determinant of the transpose is the same as the determinant of the original. No, excuse me, not doing that. A sub ji transpose is the same as A sub ij. That was the first observation we made. So I'm using the transpose to interchange indices. I'm not using that property of determinants and transposes here. I'm fishing for the right format of the thing. And that's it. There's an A sub ij. Why this thing here? A sub determinant of A sub ij, the minor matrix. You got an I plus j on that exponent of -1. So that's a cofactor. That's alpha sub ij. And we've got a sum from I equals 1 to n. A sub ij, alpha sub ij. That's the determinant of matrix A. And so we've established equation 5.2. Summing over the i's, summing as I varies instead of as j varies like we had in 5.1. So QED, there's your proof of theorem 3.1.f. First time summed over, whoops. First time we summed over j's, second time we summed over i's. All right. So we went through all of that so we could say heads held high. What we're doing here with all this symmetry group stuff and those permutations, it's the same thing you did in linear algebra. There you did things recursively. Do you like calculating determinants like this? I don't like calculating determinants at all, it turns out. But this is probably a lot more tangible than that stuff with all those symmetry groups. But this is bad too, right? How do you find alpha sub ij in either of these? Boy, you got to find the cofactors. You got to find the determinants of an n-1 by n-1 matrix. Fine. That'll have to be done in terms of n-2 by n-2 matrices, a bunch of them. So the recursion in this observation, it's actually hidden in the cofactors. and the way the cofactors are defined in terms of minor matrices. So calculating determinants is just a messy, messy thing. If only we had some tricks to introduce zeros, and we do, and you've seen those tricks applied in linear algebra. Row reduce, keep up with how that affects determinants, introduce a bunch of zeros, and then you're in business. Another topic, really, is the adjoint of a matrix. The adjoint of an n by n matrix A is the transpose of the matrix of cofactors of A. So we're going to take those alpha sub ij's mentioned above, don't like computing those, and put them in a matrix and transpose that matrix. The resulting n by n matrix is called the adjoint of A. Gentle, the author of our book, uses the word adjugate, which I am unfamiliar with until encountering this book. I'm going to stick with the term adjoint. I mean, the notation is adaptable for both of those titles, but I'm going to stick with the term adjoint. I know in other settings, adjoint is the term definitely used. Were we to go into functional analysis and look at these linearity type things, linear mappings, an idea would come up similar to this, and adjoint would be the word that we use. So I'm calling these adjoints. Be careful you try to read the book. You may run across the word adjugate. And we have a little relationship between the adjoint of a matrix and the matrix itself is given as follows. Let A be an n by n matrix with adjoint given by the transpose of the matrix of cofactors. Claim is matrix A times the adjoint of A equals the adjoint of A times matrix A, it's commutativity, equals the determinant of A times the identity matrix. May be familiar to you from linear algebra. I cover this in my linear algebra classes really quickly, and it's near the end, so we're usually in a hurry, but it's time permits, we go through this stuff. You know, that lets you find inverses of A. Hey, look at this. If we were to take this rightmost side of the equation and divide through by the determinant of A part, it's just a scalar, unless it's zero. If it's not zero, divide through by determinant of A, we'd have the identity matrix, the n by n identity matrix, equals A times 1 over the determinant of A times the adjoint of A, or A times the adjoint of A times 1 over the determinant. We got that commutativity, and that's an inverse. So we can find A inverse by taking the adjoint of A and dividing it by the determinant of A. Is that a good idea? It's a true thing if this theorem's true, but I don't see that being computationally useful because I can find the inverse of a matrix probably a whole lot quicker than I can find the determinant of it. So that makes it undesirable. Here's something else that makes it undesirable. The adjoint, that's a whole matrix of cofactors, and every cofactor is a determinant, of an n by n minor matrix. So not only do I have to find the determinant of A, I got to find, n determinants of n minus 1 by n minus 1 minor matrices to find the adjoint. We're doing this over all I and j. No, I got n squared of those things. This is nightmarish. But it's true that we can express the inverse of matrix A using determinants and adjoints. There's a little quickie formula. In fact, here's the formula in general. We can find A inverse as 1 over the determinant of A times the adjoint of A, though computationally a total nightmare. You might see this little formula in passing in linear algebra, maybe even in pre-calculus or high school, where you take a 2 by 2 matrix with entries A, B, C, D. You can find the inverse by swapping those entries along the diagonal and throwing negatives in here. That little pattern of plus minus, minus plus, totally reminds me of alternating signs that you would see in a cofactor expansion. It is. Oh, and this is divided by AD minus BC. Sure enough, AD minus BC, that's the determinant of that matrix, provided it's non-zero. So you can invert a 2 by 2 matrix with a little trick of swapping entries, introducing negative signs, and dividing by the appropriate thing. That's easy enough to check just with straight up matrix multiplication. But if you want something a touch more theoretical, it's Theorem 3.1.3, this little corollary, if you like, for a 2x2 matrix. Like 2x2 matrices, I can find determinants and I can find cofactors without much trouble.